Wonderful. Everyone can see my screen okay?
Yes.
Excellent. So happy Friday, everyone. Thanks so much for joining us today. My name is Terry Martin, and I'm one of the co-chairs of URISA's Climate and Community Resilience Committee. If you are new to URISA or our committee, you can learn more about both on the website. URISA, I'll start with URISA and then I'll get into our committee. So URISA is a multidisciplinary geospatial organization that provides professional education and training, like what we're doing right now, a vibrant, connected community, advocacy for geospatial challenges and issues, and essential resources. URISA fosters excellence in GIS and engages geospatial professionals throughout their careers. And their strategic goals are to protect, promote, and grow the geospatial profession, support geospatial professionals at all stages of their careers with essential training and resources, and to sustain and strengthen the organization. And much of this is accomplished through the amazing work of a variety of different working groups and committees that you can become involved with. All off this main page about URISA, you can go here and you can find our committees page right here. And just within our committee, we have a diverse set of working groups, including climate change and climate equity, the community resilience working group, which helped organize today's topic, policies and practices, funding and partners. So when I'm done talking, we'll make sure we add the URL in the chat and you can explore each of the missions and see examples of our past work on your own. I would like to caveat that we are transitioning to this Experience Builder site. So just know that all the content hasn't been built out yet. It is a work in progress. So I'm excited for what we are planning to be the first of many informative webinars that come out of this committee. I know we have quite a bit to cover today. So thanks for letting me share a little bit about URISA and the committee. For today, I will be turning it over in just a minute to one of our committee members, Jared Lorzell, who will be moderating today for us, and we'll introduce our esteemed panelists. So during the session, please feel free to drop your questions in the chat as they come to you. We will save them to the end just to make sure our speakers have enough time. And then if you registered for this webinar, you will get a notification in your email in about 24 hours that the materials are ready. So with that, I will go ahead and turn it over to Jared to get us kicked off.
Excellent. Thank you so much, Terry. I really appreciate that. And thank you, Wendy, for putting all this together and keeping the wheels on the URISA bus. It's my distinct pleasure to welcome Dr. John Vanderlyn and Dr. Jong Lee for a presentation regarding INCORE, modeling environment, to understand and measure the community resilience to natural hazards. Dr. John Vanderlyn is the Harold H. Short Endowed Chair Professor in the Department of Civil and Environmental Engineering at Colorado State University. Over the last 2 decades, Dr. Vanderlyn's research program is focused on performance-based engineering and testbed applications of buildings and other systems for earthquakes, hurricanes, tsunamis, tornadoes, and floods. He has also led data collection efforts following hurricanes, earthquakes, floods, and tornadoes, with the most recent being the December 2021 Midwest tornado outbreak. Professor Vanderlyn is the co-director for the National Institute of Standards and Technology funded Center of Excellence for Risk-Based Community Resilience Planning. It's headquartered at Colorado State University, and it is in its 9th year. A major portion of the COE is to develop a computational platform, INCORE, which you're going to see a presentation of today, to enable communities to measure their resilience to natural hazards. He serves as the past chair of the Executive Committee for the American Society of Civil Engineers Infrastructure Resilience Division, current chair of the ASCE's Technical Administrative Committee of the Structural Engineering Institute, and has published more than 450 technical articles and reports. He currently serves on a number of journal editorial boards, including as the editor-in-chief for the ASCE Journal of Structural Engineering. Dr. Jong Lee is Deputy Associate Director of the Software Directorate at the National Center for Supercomputing Applications at the University of Illinois at Urbana-Champaign. His research interests focus on designing, developing, and operating end-to-end cyber environments, supporting various research and education communities. He's particularly interested in the role of geographic information sciences and systems in cyber environments of various scientific domains. Current representative projects include the NIST Community Resilience Center of Excellence, where he's a co-PI with the software platform, Interdependent Network Community Resilience Modeling Environment. Ergo, Seismic Risk Assessment Systems, Great Lakes to Gulf Virtual Observatory, ARPA-E Smart Farm, Geo Streaming Platform, the API and the dashboard, and DataWolf Scientific Workflow Systems. Via those projects, he has collaborated with various scientific domains such as hazard management, hazard risk assessment, agricultural food market systems, environmental engineering, water management, computational flow dynamics simulation, sensor web, among others. It is my great pleasure to welcome you both to the URISA webinar, and welcome. Go ahead, kick it off, John.
All right. Well, thank you, Jared, for the kind introduction. And as Jared mentioned, I'm John Vandelant here at Colorado State University, and my co-presenter is Jong Lee at NCSA. So wouldn't it be great if we were able to predict damage probabilities at the individual building level and use physics-based models so that we could transfer this anywhere, not empirical models that are specific to a single structure? And then be able to predict not just how many, but which households would dislocate after a hurricane or a tornado or an earthquake, and do that based on not just the damage, but based on race, ethnicity, income, and other characteristics. And so we're able to do this with the in-core environment by synthetically allocating households from the census block level into each of the buildings. And we can do this for all of the household, all socio-demographics of the census block level down to the household to maintain privacy. And then to predict changes in community level incomes, again, by this household demographics, changes in the gross product at the community level or the tax base by sector as a result of a hazard, and have this information ultimately to make resilience-informed, socially equitable decisions. So in community resilience, we focus on 5 areas of community stability. Truth be told, we focus on the top 4 and have left governance stability out at this time. That's certainly, the political science aspect is important, but beyond the scope of the center. And so we look at population stability, economic stability, social services stability, and then physical services stability. And in parentheses, you can see this is just an example of a few metrics that we may pull from, or that are contained, I should say, within each of those stability areas. So just to show an example, to delve into a little bit more detail, looking at population, if we, this is empirically derived models. These are logistic regressions for household location in one case. And we can measure, ultimately, we can measure how many people remain. We can track them. We know if they're still in their home, but the challenge is we don't know where they go when they leave. And so it becomes difficult to measure this out-migration and in-migration flow. And so these are some of the challenges. So we think of the population stability as a 3-legged stool. And so if we think of it as, if you have 3 legs, ultimately, then it's stable sitting on it. If you have 2, then it becomes a little more unstable and your legs have to work a little for balance. 1, you're working fairly hard. And of course, with no legs, you're sitting on the floor. And so the 3 legs to the stool, one can think of as the students, the employees, and the houses, or work, school, home. So in community resilience, or resilience in general, it's important to remember that resilience is not a point in time. Resilience is a process. And so in the current state, in that stage 1, we see just our status quo, or you might be improving the condition of your community or the functionality. And then the hazard event, the immediate damage and the loss of life. And this is really that emergency response phase 2. And then the stages of recovery. And this is that interacting social, economic, and physical systems interaction that occurs often over years. And that's what INCORE models. It models this whole process, but with less focus really on the emergency response and more focus on the hazard itself and then the recovery stages. So to do this, it begins with an integrated community model. This is building archetypes. These archetypes are representative of buildings within a community or a city, and they are assigned based on, depending on the hazard. There's different suites for different hazards. The transportation network, the water network, as well as power networks. And these are essentially put together using graph theory. There are some flow models, but they're not broadly used in the basic structure of INCORE yet. And then a computable general equilibrium model, which I'll explain a little bit more later, for the economy that you see on the top right, and then the social institutions, and that's the hospitals, the schools, things like that, as well as the households themselves. And so, as you heard in Jared's introduction, the interdependent network community resilience modeling environment, that's INCORE, and it focuses on the physical infrastructure, as I mentioned, the economic health of a community, the social services, and this is all done, as John will explain in quite a bit of detail later, the information science, it's all done within a cloud computing system. And so once we have that initial community description that I described on the last slide, we then look at the damage and loss from the impact of a natural hazard. And so it can be a flood, it can be a hurricane, it can be an earthquake, it can be a tornado, as well as several others. And then modeling this multidisciplinary recovery, and this is with the integrated databases. And the whole idea behind this is to look at alternative actions to enhance community resilience and inform planning. So to look at what-if policy scenarios. So I don't expect you to run through this in detail, and I'm not going to either, but this is sort of the conceptual structure, and this has been around for about 5 years. It's been modified a little bit, and the basic idea, we'll come back to that a little bit later, but the economic modeling and analysis, as I mentioned, this uses a spatial dynamic computable general equilibrium model. It incorporates infrastructure damage and population disruptions, and that's why it has to be spatial, and then can look at a range of economic and fiscal impacts. So, for example, design code changes, can look at different scenarios, and then includes things like the loss in production at the community level, wages, jobs in local economic sectors. And the idea is investigating policy levers, looking at optimal allocation of resources coming in from the federal government or investment or whatever it would be. Social science modeling and analysis, this is really population and employee dislocation, housing restoration and recovery, and then focusing on business interruption, which of course then links and affects the economy. And this suite of tools can also identify socio-demographic and socially economic vulnerability characteristics. So thinking of the household model, we can then begin at the census tract, go down to the census block level that you see on the right, and then we can synthetically allocate things, and this is just showing the synthetic allocation of the household incomes for a census block. We can do this, whether it's female head of household, whether the family owns a car, of course the race, ethnicity, all of these things can then be synthetically allocated to build these synthetic households that would, if aggregated back to the census block level, reproduce the census. So looking at an example, the city of Joplin, Missouri, was impacted by a massive EF5 multi-vortex tornado. It was the deadliest, costliest tornado in single tornado in U.S. history, and the deadliest since the advent of Doppler radar some 50 some years ago. And so we'll focus on this example just in the buildings and the electrical power network. And so we can see some of the population, some of the other items down there, and then, of course, the outline of Joplin on the right. So on the left, we have a suite of 19 building archetypes that were developed within the center. This was done early on in the center, and for tornadoes. And this, on the left, you can see the archetypes. Of course, a large portion of them are residential, as you can imagine, and then other types of buildings toward that business corridor that you see in green and blue and things like that. And then the housing inventory, unit inventory on the right that we can see. And that, of course, helps us do the synthetic allocation. On the left of this slide, you can see in the large blue circles are the electrical substations. There's 18 of them. And then a cellular automata algorithm selects the service area based on supply and demand, whatever that substation can provide. On the top right is the social, it's a simplified social accounting matrix. And this is just showing, it's essentially used as the input to the CGE. And this is this large amount, can be hundreds or even thousands of interacting differential equations. And these are put out of equilibrium with a shock, which is the earthquake or the tornado in this case. And then a solver solves all of these equations to then balance it and decide once it's in equilibrium, then that's the new state of the economy. And that's how it's predicted. And then the population dislocation algorithm, and this just shows going from the building damage or building loss, percent loss in this case, the population dislocation regression, and then going all the way to, so taking into account the damage, the race, ethnicity, as well as the income. So what do we do with this? Well, so here's an example. We can look at different retrofit strategies. So on the bottom left, this is showing 3 different strategies, and the structural details of this isn't terribly important. I'm a structural engineer by training, so that's why this is one of the examples that we developed. But what this does is we can see on the right that this is showing the functionality, the results. And so if we use retrofit strategy 3, 41% of buildings within the tornado path remain functional after the tornado, whereas almost none if we use retrofit strategy 1, which is actually status quo. That's just a typical house in Missouri. We can also then look at comparing retrofit strategy 1 and 3 and look at the socioeconomic metrics. And so on the left, you can see the changes in employment, domestic supply, both for residential, commercial, as well as household income by household income level. And interestingly, these vary quite a bit. But to give you an example, we can see employment in the trade sector reduces by $742 million. And keep in mind, this is a small community following the event, whereas, and so that's essentially what was predicted to happen or did happen. And then only 443 million if we were to have this retrofit in place. We can also look on the right, we can see the population dislocation and how that changes between retrofit strategy 1 and 3. And you can see it's fairly significant. It's still not perfect simply because this is a very large tornado or strong tornado. And then we can also deaggregate. And so we can look at community level goals and we can say, what should we do to the individual structures or the individual facilities from a physical standpoint to achieve social and economic metrics or goal, really not via metrics, but goals at the community level. And we do this through a sort of a deaggregation. It's really a checking it going forward. And then once we find that value, we've effectively deaggregated it. So we can look at generic tornadoes. These are EF2s, so that's a weaker tornado than actually occurred. And the idea is, just from a planning perspective, we would be helping communities that perhaps never saw an event, but are planning in case there's an event. And then we can set up our physical service metrics, our population stability metrics, and our economic stability metrics that you see on the table. And we can look at different tornado intensity levels, and this is from the NIST Community Resilience Planning Guide. These are not the EF categories, but the terms routine, design, and extreme. And so it's designed for planning. It's not something that you would always design for, but if you want to focus on community resilience, then something called the design is recommended. And then we would call these goal A, B, and C. And so you can see they get more stringent. We want 98% for the smaller event. And the community may never see that, but this is the planning. And then you can see just 1% dislocation for the smaller event and 5% for the very large event, which is an EF4 tornado. And again, just doing it that way. And so we can compare the original design and the retrofit design. And if we do that, what happens is we can see that this is just showing if we randomly, spatially random retrofit of residential structures only, wood residential buildings. And we look at 40%, we look at 80%. What it turns out that the population dislocation metric or household dislocation metric controlled the retrofit. And so we would want to retrofit 34% of the residential structures to be able to achieve all of these metrics at all three of these tornado intensity levels. So another thing we can do is we can look at the residential building recovery, and we can also look at commercial recovery. I won't be going through that today, just in the interest of time, and we do this by looking at and so these are a lot of these physics-based models that are in NCORE. This is just some examples that our groups have done, and looking at the household restoration. And this is really where the statistics change based on where the insurance money comes from or where the financial resources come from. And so we can see that in here. It's reflected. And then this approach, it looks at these three delay phases. And so these are known as impeding factors. And so we can look at a number of different cases of policy change. We can say, okay, if we just looked at the retrofits, which is the one we looked at earlier, what does that do? What if we looked at everything? We said, well, once an event occurs, we'll relax building permit issuance for residential structures only here. So we wouldn't do that for commercial, of course, it's too dangerous, but hiring extra building inspectors, things like that. And that all goes into the statistics and then the model processes. And you can see ultimately after 3 years, everything converges, but there's quite a big difference between case one, which is just doing nothing, versus say case 6 at the 1 year point. You would be 75% recovered, whereas you'd only be 10% recovered if you did nothing. So just to jump to now a flood example. So this is obviously North Carolina. This is Lumberton, North Carolina. We've done a field study there. So Hurricane Matthew started as a Category 1 storm. It became a Cat 5 storm, as you can see down at the bottom of that image. But ultimately, it weakened and then sort of skirted the coast. And so you can see it barely came ashore, really just touched the shore, or at least some of the bands touched the shore, but the amount of rainfall was quite significant. And so we have a notebook, and I think John will be explaining some of these things in detail in a little bit. But and so each of these, we have a number of test beds as well as community partners, and so each of these has a Jupyter notebook that essentially runs NCORE. And so these are the items that are within this one. So we look at again, as I mentioned with the tornado, we had a suite of fragilities that was developed specific for that. The same for flood. These are some of the most advanced flood fragilities in the world currently, and they were developed differently. They weren't done empirically, and so that you can see they were done with extensive data collection. These are some images from Lumberton, and this is just showing your damage states. And then here's an example just for a single family house, and this is not everything. And so you can imagine for the hospital archetype, for the schools, things like that, and for the big box store, how involved these are. And so this is really pulling together all of the statistics and things. And so this was and so there's 15 of these. And this is just showing the theory behind the method, essentially just an example of 5 of the component fragilities, which then map into and form the structural or the full building fragility. And this was done looking at loss analysis, looking at a number of different sites with predictors and adjusting, and it can, of course, can be adjusted for location as well. And so this is the 15 archetypes, not to scale, obviously, with each other, because we wouldn't expect the 2-story house to be bigger than the hospital. And then just showing for a very simple representative 1-story, 2-bedroom apartment. This might be like a public housing unit. Showing how we would then these would be just some of the components. There's a lot more, of course, like the carpet, the drywall. And so these were used by the Office of Management and Budget to look at the exposure of essentially increased costs and lost revenue due to climate change for all government-owned buildings. And this white paper is out there from as of March. And then just show a few of the BIM models. This is a sort of like a Walmart or something like that, a strip mall. Just a generic office building, 2-story school, health center, maybe a clinic. Could be a small hospital if it's a small enough community. And then a community center or a church style building. And then, and so then we put these in, and so you can see an example of how they're mapped. And so then going back to Lumberton, this is showing the mapping for a simulated flood in Lumberton that was validated. And then we can look at different types of mitigations. We can look at adding floodgates or temporary berms and what the effect is on the flood. And we can look at enhancing the current levee system. And so we've done all of these studies for the Lumberton model, and you can see the changes on the right. And we can even look at retention or detention systems and see what that effect is. Those tend to be a little bit more costly if actually a lot more costly if the topology doesn't cooperate. And so then this is there's a mapping algorithm for flood. And so this is showing, and it's basically just a set of a large set of rules. And so you're seeing 500,000 buildings, Santa Clara County in the Bay Area of California being mapped. And then we can simulate that flood for Santa Clara, the one that occurred about 5 or 6 years ago. We've not been able to do an exact validation of this one because my understanding is there's quite a few lawsuits pending with the city or the county, but visually it's accurate. All right, and with that, I will pass to Jong to run through almost the remainder of the presentation. Jong?
Yep, thank you. So I think you saw all this analysis and also research is done using the INCORE. I'm going to show you a little bit later, but all those things are done by the Python interface and Jupyter Notebook, which means that some of our stakeholders, they don't have the faculties or they don't have resources regarding this kind of technology. So there was a request about, is there any easy way to use InCore? And then after we got the request, we start to looking into what's a good way. Then we identified this playbook, NIST playbook, as a community resilience planning kind of summary of the entire community resilience planning guide. And it provides the 6 steps that each community go through these 6 steps that are able to build community resilience planning. Next. So what we've done is then using the 6th step, which is in the below of integration, and we identify where InCore technology or modeling can fit in. So after we identify that, we are able to build a web application that planners or emergency planners or community resilience officers, they log into the system. They still go through these 6 steps, but when the InCore technology required, the InCore technology can be used, they're able to execute some of these modeling efforts to our NCSS server to run those analysis. Next. So this is some of the example that we also already built their web application. So it's a Galveston, Texas. You can see that there is the Galveston area is a Galveston Island, which has a lot of recreational activities currently going on, and some of this demographic information here. And we work with the city of Galveston to help them out how to analyze community resilience of their city. Next. So the first is the hazard modeling. Galveston, Texas, are exposed to many hurricanes. So these are the currently InCore support the intensity measure of the hurricanes. You can see surge height, significant wave height, inundation duration, and wind speed. So you already see that this is a multi-hazard effort that we utilize this to analyze the damage estimation and recovery and socioeconomic analysis you saw for the other test bed. Next. Some of the community model of these archetypes here that we adopt archetype for the from the flooding, but this is also some archetype is overlapping with a tornado, but utilize the archetype to develop the fragility curve for this archetype. Next. And then this is basically what we've done is it's a real community, and then we acquire all the building footprint of the community and then try to show that all those building data is in InCore, and then we're able to execute this modeling environment. Next. So some of the risk analysis here, you can see that the colors represent some of the most dominant damage states. You're able to see red dots shows that there's many buildings are very vulnerable in terms of damage states. And obviously there are a lot of blue dots which is in the inland side of the city of Galveston. So it shows that we are able to do this risk assessment of the building damages in this area. Next. And similarly, this one, I believe that shows that another area of the island there. So you can see some of the buildings are, could you go back one thing? So you can see there's a lot of blue buildings, even if they're in the island. The main reason is there is the protection, John, I forgot what it calls, and the seawall. Yes, seawall is actually built front of the island. So that's how those buildings are actually a blue, which is lower damage state in this case.
Yeah, that's correct.
Yeah, thank you. And also this one shows the roadway and bridges availability, and we are able to do damage estimation of the bridges and roadways, and also that actually connects to the building accessibility. So we are able to compute the building functionality due to this transportation accessibility, and then later on the power availability and things like that. Next. This one shows the result of the dislocation and also access of the road and bridges. So you are able to see on the top view about some of this location from inaccessibility in terms of power and transportation or both. So the building does not have the power and transportation, really the building is not functioning. And then so that the household or population will be dislocated from the building. And then below, you can identify also why dislocation is causes because of actual structural damage or inaccessibility or both. So those information you are able to extract from the result of the modeling or run of the in-core analysis. Next. So this is a quick video clip of the community web app application that you can log in. And then you can see the left side, there is 6 steps that user can follow. And each step has, sometimes some step has just a documentation. This step 3 days 3 is actually able to define the scenario hazard of the community. So you can upload the hazard data set, which is usually raster, or you can actually look at the existing one that when we work with them to define. So in this case, you can see Hurricane Ike or some other scenario hurricane. So if you click on it, you can see there's many geospatial layers coming from the in-core server. Each layer represent the intensity measure in this case. So you can navigate and understand what kind of hazard we can use in this analysis. And the next step is you're able to run the analysis. So when you run the analysis, there's several things you can define in terms of data and everything. Right now, we are showing the result of analysis. You can look at the building functionality in this case. So in this visualization, we show you the category of the building, critical facility, emergency housing, housing neighborhood, and community recovery. Those building categories are defined at NIST playbook. And also it shows the building functionality, which buildings are functioning, which is not, and we categorize by this building categories provided by NIST playbook. So you can see that community recovery buildings have the heavily non-functioning. And this one shows the population dislocation information, especially you are able to navigate through population dislocation with the different categories by tenure or by race and ethnicity or by household income levels or housing types. So you are able to identify which population demographic populations are more vulnerable in this situation and things like that. And the next one is, this one is a CG model that John already explained. It shows economic impact. In this case, you can see we able to see the inland and island economic impact before hurricane, after the hurricane. So you can see the green bar is before the hurricane, the red bar is after the hurricane. So you see that how much the economic impact because of hurricane in the various category. This one shows the employment, and then also you can see the domestic supply and household income and things like that. Okay, next. So the web application you just saw is built on this architecture here. So this is very general architecture. I can start explaining from the middle. We have in-core web services. There's various services we have. It's web services that first a hazard service, DFR3 service represent all the damage functions and fragility curve and repair curve. And those curves are stored in the database we expose through the web service. And then thirdly, data services, all those like building inventory, infrastructure inventory, demographic informations, all that stored in the data service. And space and user service control the access. So you are able to grant access to other users, or you can restrict access to your data or results. And plotting service provide some of the plotting the chart of DFR3 curves. And GeoView services basically is OGC web map service to provide the geospatial visualization of your data set or result and things like that. And those web services are, it's a REST endpoint, and then it could be used by the PyIncore, which is orange box. PyIncore is Python packages. So we have a PyIncore package and visualization package and data package. It is a collection of the classes and method user can use, especially PyIncore package contains all the communication with the web services and also all implemented analysis in there. So if you are interested in how the building damage analysis are implemented, you can look at the PyIncore GitHub repository. You'll see all the algorithm in there. So currently we have about 40 algorithms that we implemented as an analysis. You're able to see all the source code in the PyIncore package. And also the orange box is called Incore Web Tools, because the web services are not always user-friendly. So people want to browse and then looking into and download those data. So we provide the viewers, the lightweight web tools, the data viewer, able to looking at the data service, user can search and browse and download. Hazard viewer is looking at connect to the hazard service. DFR3 viewer connect to the DFR3 services. And all those things can be also used in the Jupyter Notebook environment, which we provide in Core Lab. It is the Jupyter Lab environment. So you are able to log in, and in NCSA server, it creates your own Jupyter Lab environment, and you are able to do scripting and modeling using the PyIncore packages within NCSA server side. And all those web-enabled services are implemented on NCSA cloud system. We are utilizing Docker and Kubernetes. Next. And these questions we always got, what is the strength of Incore? Because there are some of the other tools and softwares out there. So this is some of the points that we identified throughout our experience with the researchers. First part is Incore Python API is very consistent. In other words, that when you execute the building damage analysis in Incore Python library, breach damage analysis or other analysis are very similar pattern how you can set it up, your analysis within the Python code. And also it allows us to chaining different analysis next to each other. So building damage analysis can output of building damage analysis can feed into building functionality, and also building functionality could be fed of the result of like a power network damage analysis and things like that. So it can be, each analysis can be chained. Second part is Incore supports very popular generic data format as an input and output, some geospatial data format and some of the tabular format. I'll get into more detail in the next slide later. And thirdly, Incore Web Service provides you and the latest data information, which means that we maintaining our database and web services. So whenever there's a new data or data is updated, then everything is reflected to the web service. And we also regularly announce with our release schedule. So if you are in the part of our mailing list, you'll receive what is changed, what is updated in terms of data and functionality of Incore. And fourthly, Incore can be integrated or integrate other Python technology easily. You know, the OpenSeas is one of the popular tools you can create the fragility curve, because it's also a Python implementation they have. Incore and OpenSeas can be work together. And Winter is a Python library developed by EPA about the water flow analysis tools. It's a Python library too, so you can also very quickly Incore and Winter can marry together to use together. So obviously it requires some of the manipulation of the data, how the input and output going to be, but that can be very easily done if you know the specification of input and output data. By the way, Incore provide all the schema and or the definition of input and output data in our website. And next point is Jupyter Notebook examples. In Core, we publish many Jupyter Notebook examples, including some of the testbed you saw John explain to you, that you can find actual notebook in our website, which means you can download the Jupyter Notebook. For example, Joplin testbed, you are able to execute on your local machine on your Jupyter Notebook, or you can upload the Jupyter Notebook to our in-core lab in NCSA. You can actually execute on our server side. But no matter what, our research is very transparent, and also reproducibility we already built in because of Jupyter Notebook. Lastly, open source means that you know how it runs. We also got some of the question about algorithms. We shared with them with some papers and our publication, but at the same time, we are able to share our source code where actual analysis happens. That really brings a transparency, and also that opens up that how we can improve our algorithm better with more people can involve it together. Next. And some of the next two slides, I try to explain some of the geospatial capabilities. As you know, InCore is inevitably is all geospatial data we deal with. So there are many data that are geospatial and or georeferenced. So we support the GIS data format, such as for vector, ESRI shapefile, and geopackage, and raster is mostly geotiff. Recently, we start to moving toward the geopackages. As you know, that ESRI shapefile is really well-known format, but there's some of the limitation it has. But geopackage is OGC standard format and already supported by many GIS software anyway. So we are slowly moving into the geopackage support right now. And thirdly, Python PyInCore packages, we utilize well-known geospatial libraries. In terms of data and visualization, we are using GeoPandas, Fiona, and raster.io. And visualization side, we use a Folium or IPyLiplet on the Jupyter Notebook side. So some of the screenshot you see in the slide is this is all in the Jupyter Notebook. So you can see that some of the tornado path here and Joplin's damage estimations and functionality estimation, and then also recovery estimation on those OpenStreetMap visualization. It's interactive. So you just click on those points or polygons, they're able to see the attribute on the Jupyter Notebook. Next. The next capability is the server side. So we provide the geospatial visualization service, but this is actually a OGC web map service. We currently utilize a GeoServer, the open source product, provide web map service. So what happened is user upload the data to the data service, and the data service create GeoServer WMS layer using the data. And then that one has a data service data set and GeoServer layer use the same unique ID that we know when user said, oh, give me this certain data set. And we know that if that's a geospatial, there is the same name, same ID geospatial layer is available in the WMS service. And this OGC WMS layers is currently used by PyInCore directly, like you saw before in the Jupyter Notebook, or currently is used in Data Viewer. So you log into Data Viewer, and there's a little icon, is a map icon, and then you click on it, there's a preview button, and it shows that data preview, so you're able to see where it's located, what kind of data set that is. And also the data service side, we implement all the GIS capability using in the Java. So it's a GeoTools and GeoServer clients and several raster data management libraries we use in the Java side. So we are fully utilize very standard GIS specification. GIS libraries follows OGC specification. Next. So this slide is a summary of some of resources. There's a landing page, and then there is a documentations. Documentation has a lot of tools and tips and all the Jupyter Notebook I just mentioned. And we do have a GitHub repository. You can please come and see that all the source code we have. And we publish the Python package through the Conda management system here. And then we have a support email. Oh, actually, I forgot to add that we have a public Slack workspace. So after that, maybe I can send out the email about how you can access the Slack channel. Next, I think that's the last part. Okay, John.
All right, thanks, John. So kind of going back from the technology and InCore itself back to really, what it's able to do from a science perspective. It's resilience analysis requires the modeling, but from before, during, and after the hazard event, and such as the flood or the hurricanes that we showed, or even the tornado, and modeling the physical building and the network to this event, this network damage of water networks, electric power, that no matter how comprehensive this is, it's just a portion of the story. And so we like to think of it as really, what we're building is, a digital twin before that term was really popular, but it really can't be seen. It's the economics and the households and the people. And so being able to comprehensively measure resilience in terms of these 4 stability areas that I mentioned is critical to be able to look at what if scenarios under a changing climate or to an earthquake or whatever the hazard is for communities. And so it's really about these what if scenarios, and then improving resilience through communication, decision, and these actionable strategies. And so resilience is about people, equity, safety, and working to improve the quality of life. And INCORE is able to do that and really look at the real cost of an event, not just the dollar loss. And so I want to mention we have on the website, we have a number of briefs. We call them community briefs, research briefs, and then just general briefs on kind of workflow and things that you see on the right there. And we're working on more as time goes on. And then lastly, just INCORE.org is the essentially a nonprofit that is working to use INCORE to help communities. And so this is a fiscally sponsored nonprofit out of community initiatives in Oakland, California. And so we're starting to do some projects to assist communities using this technology. And so if you're interested in learning more, you can scan that code there, or just INCORE.org will get you there. And then finally, the center over the last 9 years and 1 more year has been funded by a cooperative agreement between Colorado State and the National Institute of Standards and Technology, and we're grateful for that. And with that, thank you.
Excellent. Thank you so much, gentlemen. That was very informative, and we'll go ahead and open up the floor for questions right now. Does anyone have any questions they would like to ask our panelists here?
And I saw in the question and answer, there's a question is, do you consider measuring emotional damage recovery? As far as I know, John, we don't have that aspect in our INCORE modeling.
We did so former PhD student of mine who's a associate professor at Kansas, her dissertation here was on the effect of, it was basically on the trying to quantify the effect of post-traumatic stress disorder after an event. And so the modeling, it's difficult but not impossible. So that is something that, that is essentially something that could go in there. We've not put it in simply because the validation, with HIPAA laws and other things, the validation it's quite aggregated, and we work at the individual household level. So we don't have it in there, but it does make sense that something like that, that's looking at things like like a lack of presence at work. So you're 60% productive at work, and what's the effect on the economy? And then of course but we don't look at those adverse health effects and things beyond having looked at it in a research perspective. But the short answer, as John said, is no, it's not an INCORE now, which I probably could have led with.
Let's see. We have any? No other questions from the audience or the attendees? We do have one here. What is the building database you're using in INCORE? And is it specific to a region, or is it a national data set?
I can answer first, John.
Yeah,
so when we start, it's specific to the region. So most of the data sources coming from their GIS department or tax assessor's office. That's the main data set. And we later on, also Atom's data set, that's what we used to, right, John?
Yeah,
Atom data. And then later on, we also start to utilize the national database, NSI database, National Structure Inventory Data. So that's another data set from Army Corps of Engineer, I believe. Then the one issue with NSI data is that some of the information in the data are masked, which is not available, or is aggregated in some ways. So that it can be still useful data. So we utilize different sources of data to create better data for a certain region of interest.
Excellent. And I'm going to assume that will feed into the building attributes and the archetype. layout that's been used in NCORE.
Yes.
Fantastic.
Yeah, and that's right, Jared. And that's essentially how it decides which archetype to map to. And that's the most well, for the initial damage description, that's really the most important part is describing that. And then of course describing the household. It's all done sort of at the same time and built into that initial community description.
Excellent. So this is all free to use for folks. If all they have to do is go to the incore.org website, sign up for to a membership, and then
Yep.
and then I'm assuming there's area for a usual user manual and basically instructions on how to run through the PyNcore Jupyter notebooks.
Yes.
Yeah, that's right. And there's a Jong, I believe the Slack channel is public now. So
Yes.
there's a Slack channel they can join and ask questions. And there's weekly office hours or weekly office hour by NCSA if there's questions that pop up on how to use it or how to do something. And of course they can always, and then we'll be hosting a number of workshops over the next 13 months, probably at least 3, if not 5. In different locations. We just held one for about 40 people in Washington, or actually in Arlington, Virginia, about 2 weeks ago.
And we also posted all those workshop materials so people can still follow some of our tutorials.
Oh, that's fantastic. So, so in terms of data, can users integrate their own data sets into NCORE?
Yes. So that's actually a very common question. So you are able to use your own data, but each analysis and also data set has some required schema, and we call semantic service. As long as you follow that schema, it runs with NCORE analysis.
Excellent. So a community could incorporate their own updated data should they feel necessary. Doesn't quite match with the census anymore, or they would rather see maybe some planning information added to it that isn't quite represented in any other data sets.
Yep.
And you can even take a data set and change it. So you could say, okay, what if I made every wood building a masonry building, and I change the archetype, and then you can use it within your own notebook for yourself and just keep it, or you can actually, like John's saying, you can actually create using the semantic service, the actual data set, and generate it.
Fantastic.
John, hopefully I'm saying that correctly, but
so I don't see any other questions from our attendees. Terry, did you have any concluding remarks?
I do. I just have to come off mute to do that. So I will go ahead and start to wrap us up here. We're doing amazing on time. You guys really killed it with getting us to the 2-minute mark. It's amazing. Okay. So I'm going to try to share my screen. All right. Awesome. So hopefully you can see that and not all my Zoom bars. So first off, thank you all so much for attending today. And thank you to Jared and our amazing speakers. This was absolutely fascinating and would be such a valuable resource for communities. I'm so excited and really appreciate John and Jong and Jared for bringing this effort to our community. Really excited to be able to spread the word, let folks know that this is something that they can play around with and hopefully support moving forward. So thank you all again. Before we wrap up, I did want to mention again that first the webinar was recorded and the speakers have graciously offered to share their slides as well. If you registered, you'll be receiving an email in your inbox in about 24 hours that includes the link and all that information. So that's all coming your way. We have a lot of amazing events coming forward. So as you can see on your screen, we have URISA has put together the JS Leadership Academy is coming up, already planning for GIS Pro 2024, and a lot of other really amazing events, the LEAP Conference, CalGIS, the GIS Valuation Technologies and Conference. I don't know when Wendy sleeps. And then our community resilience working group and the Climate and Community Resilience Committee is putting together a lot of webinars moving forward. So we hope you'll tune in for that after the new year. Starting off with FEMA's Hazardous and National Risk Index. There's a lot of cool updates coming to HAZUS that I think anyone that's on this call and all the things that you all talked about today would be likely interested in hearing about that, as well as the wrapped updates, and that'll be in February, and then the role of GIS in determining the FEMA Community Disaster Resilience Zones. All really fascinating topics that we have coming your way. So please visit the URISA website if you're ever interested and want to make sure you're not missing any of these topics moving forward. So with that, I hope you all have a happy and safe holiday season. I can add my contact info to the chat in case anybody has any questions following this webinar. Please feel free to reach out. Look in your inbox tomorrow and you will be seeing all the info from today. Wendy, Jared, do you have any final remarks?
Other than to say to thank John and Jean for that great presentation, and I'm hoping everyone that was listening today will at least investigate INCOR and check it out.
Agree completely, and thank you to you all.
Thanks so much.
All right.
Thank you, everybody. Have a good weekend, and thanks for hosting.
You bet. Thanks a lot.
Bye.